Okay, we're starting. It's happening. It will start now. The next talk is entitled Understanding Admixture Analysis, and it will be given by Emil. Emil, on you go.
You recording me? Okay. Well, hello. Yes. Understanding admixture analysis, which together with John Fust and Meisenberg, who apparently is not here. So, we've seen this thing before. There are large group differences. Some of these are national. I used the national just because it's a nice map. And these have contested explanations, but if you look across group differences in many countries, it's obvious they're kind of racial in nature. They might not be a specific race, but it's like a mixed group, or like Hispanics are not exactly a race, but it's a they have racial ancestry from Amerindians and European and some African even. So there's definitely a racial component to it. And sociologists have been noting that this kind of is reflected in the skin color. And they talk about the pigmentocracy, skin color control. And it's a big theme. So we also know that they're quite stable over time. And this is a meta-analysis work in progress. It's like the update on the Broth 2001. Except that we plotted all the data all the way back on the timeline. And so this is kind of a heterogeneous sample of about 100 of these gaps, going back to as far as you can even go back. Some of these may be unknown to you, but we found these gaps even back together before any tests were invented. And it comes from these very simple reading assessments that you actually get from the census. Like, can people sign their own name? You can get like a proportion of people who can sign their own name, which is kind of a very primitive verbal ability test. And so even the gaps under slavery are they're somewhat noisy because small samples, but they're fairly in line with the later ones, which is incredible, or very depressive, or very non-depressive either way. If you do just straight regression line, this is the yellow one. I didn't make it flat on purpose, it's just exactly flat. If you take these data, and the blue line kind of shows how it moved up and down. There's a big debate about the causes of these gaps, which I think we will listen more about in the next talk. And basically, if you ask a bunch of experts, that Heiner and David and Coyle did it, you get something like the mean estimate is something like 50% for the US black-white gap, and maybe 20% for the international one, something like this, genetic. The others is like attributed to a variety of environmental causes. There's some funny things with these, but I think the next talk will go into those. So, there's also a debate about whether these mixed populations follow the pattern expected by genetics. And it's very simple. In a simple genetic model is that intermediate populations should always be in the middle. And whatever degree of intermediate population you are, if you're a 50% person, you should be 50% mixed between Euro and African, you should be in the middle. If you swap to some other groups, Europeans and say Eskimos in Greenland, the 50% should also be in the middle of these, and 20% you should be towards one of them, and so on. There are a bunch of studies that are often cited, but quite weak. We have a very small study from the 30s. They found gifted black students in the, I think it was in Illinois or one of these northern states. And they asked, these children are, if white ancestry or European ancestry makes you smarter, they should show elevated levels of European ancestry, which they supposedly didn't do, at least according to the authors. There's the famous German study, IFTERF, from 61. They looked at post-World War II, US troops were stationed in Germany, and some of these intermingled with the local German women, and this produced some offspring. And some of these US soldiers were black, and so they got half-black offspring, or Mischling as they write in German, and some of the other ones were white. And so they could look at the gap between these groups, and supposedly there's no gap, or it's too small, and that's very common to see this one if you read like Nisbet or one of these people. Scar et al. Did the first, as far as I know, sort of modern attempt to look at admixture. They used a bunch of blood groups you can get before you had like total DNA sequencing. You could get like small proteins, and you can get blood group estimates, and this can be used as a kind of crude admixture estimate that this person is probably 20% African or 35% or whatever. And they didn't find any correlation with IQ in their sample, or rather there was one, but it was very small and too small, maybe.
One short comment. In the alpha study, the soldiers are not pre-selected?
Yes, they are. That's an interpretation issue. So the black soldiers, because the US Army has in each IQ test to get into the army, so the German, the black soldiers will be above average from the black mean in the US. So it gives you a small expected difference.
Would you like this one?
No. Yes, the evidence quality is quite poor in these old studies, at least these are studied. And as Heiner was writing in his book, single studies are always suspect. And especially they never replicated these old studies. And like, who studies for a highly important scientific question? Who thinks evidence from like one study from 1960 is sufficient evidence? It's not rational. Some of these are very small. This one was the one with the black, if gifted kids. It's only 60 kids in one state in the US. No one should have a strong opinion. And it doesn't matter what they find. With 60 sample size, you can find anything. And the ancestry in the old ones were dubious. Sometimes they used family history. They just ask you, oh, how many of your grandmothers were, this or that group? And as we all know from family history, sometimes when you check it, it's not true. Lots of people claim in the US, they claim some kind of Indian ancestry, and then the DNA test comes back and you can see it's all like 100% European. This common thing. There's very likely to be major publication bias and probably some questionable research or practices other than this, because we know that these are basically omnipotent, and the more political it gets, the more they are, and they also go in the direction that researchers have, and we know which direction that is because there's tons of these studies about the left-wing bias of academics. So we know which way the bias is expected to be in, and we know the evidence basis is poor. It's a very bad basis for drawing any sort of conclusion. There's actually a lot of old data and other data that was summarized by Shuey in the 60s, and also Jensen did it in 73 in his book, but it seems that no one has bothered to summarize these studies, meta-analyze them properly, but it can be done, and I've just initiated with John Fuhr's the meta-analysis of these studies, all the pre-genomic studies from the 20th century, including some in Spanish and Portuguese, which you can apparently find as well from South America. There's ones from Aborigines in Australia too. So we're trying to get Malloy data.
Oh, good, good. Brazil's got to get a look in.
Yes, but genomics is upon us, and here we see a person that might be here today, and it's from 23andMe. So 23andMe, you order it, they give you like a small spit kit, and you are not supposed to eat for a couple of hours unless you want them to sequence you and find your chicken. And yeah, so sometimes, I don't know. So you sit and spit in this for about 5-10 minutes, and you send it back to the US, and sometime later they send you an email and say, your results are here, and it's been called the racial purity test, and which is funny. It costs about $100 to get one of these. I think there's a sale right now, it's only $80, so I recommend getting one because it's fun. And later you can use the data from this to make predictions. Right now they make a bunch of predictions for you, 23andMe. They're mostly useless. It's the only one they make that kind of makes sense is the ancestry ones. And you can download your data and upload it to some other company that gives you better predictions. So you don't need to pay for their extra predictions. But if you go like large commercial scale price for this microarray data, it's about $25 per person if you scale it, if you do like a biobank. So if you had like one rich person, you could easily build a biobank. It's not that expensive. You can collect data online and build a biobank. But to really understand admixture analysis, you kind of need to go back to the basics of genetics, statistical genetics. And so I simulated a bunch of data to get a better intuitive understanding of this topic, and I'll take you through some of these simulations. So, you've probably heard of polygenic scores. It's just a score where you basically sum your genetic variants, whether they give you more IQ or less IQ or more height or something. The trait doesn't matter. You can score this. And here, we pretended that there are 10 loci, 10 spots in your genome that has something that varies, a variant, that if you have it, it gives you 1 point, and if you don't have it, you get to 0, and all of these have the same frequency, 50%, and of course, this gives you an expected value of 5, which we see is the expected value here. In this case, I've just simulated 2 groups, but they don't have any differences aside from random chance, so that's why these are basically all the same, sample size depending. And if you just keep adding more of these loci, eventually you get a normal distribution by the central limit theorem. So you get something that looks like this. This is the same as before, except I added a little random noise, and that's basically in nature as well. If you do identical twins, which have almost identical DNA, they're still not exactly identical in any trait, even when it's highly heritable, and it's because there's just some stochastic noise, biological variation, and possibly some actual true environmental things going on. And this gives you a very normal looking distribution, here again with no group differences. So here we do the same thing as before, except that now we say that there's a group difference, that the frequencies for the group 1 or A, the frequencies are now 0.55 for all these 10 loci and 0.45 for all of them. So it's only a 10% point difference in the change that you get the positive allele, but because there are 10 of them, it translates into this group difference you can see, which is now 1 point on this arbitrary scale. So now we made people at random. So we start up with the two groups that are here. They're both pure in this group, and they vary in this polygenic score. I added some more of them here to make the numbers nice, but the scale doesn't matter. And so you see this group is higher. The mean is 5,5, and it's 4,5 here. And then we just made these people at random. This produces a lot of people in the middle with somewhat around 50. Not exactly 50, because when you get DNA from your parents, it varies a little bit exactly who it comes from. And so you get some variation around 50. And of course, some of these people were just people who made it within their own group. The mating is completely random here, and the groups are equal size. And if you keep doing this, eventually you can see the correlation decreases between ancestry and polygenic score over time, but you can still see the slope is the same across the simulation. So the correlation is the wrong unit to use because it's standardized and it depends on the variance in the admixture. And the variance in the admixture differs randomly by who you're sampling, how admixtures they are, the relative group sample sizes. Correlation is the wrong metric. What you need to look at is the slope. The slope is constant. Even it doesn't matter how you admix people, exactly the proportions of groups, it doesn't matter for the slope. The slope is what you want.
You would also call that the beta.
Yeah, the beta from the slope.
Yeah.
So, large data sets with genomic data, they do exist. And in fact, some of these have both IQ, skin tone, and self-reported discrimination, so you can actually just plot all of this into one regression model and you get the final answer to these questions, more or less. And there are some like UK Biobank, which somehow has skin color, and Pelotas is a Brazilian data set, which is easier to get, but there's actually a bunch of other US ones, and I compiled like a big spreadsheet with all these data sets if someone is inclined to apply for them. The data are basically all public, or all hidden, almost. There have to be strict rules to apply. Only professors can apply, not a PhD student. You have to get a full professor to apply, and you have to go through an IRB sort of thing at the university to get all this restrictive data. And I'm not a professor, so I can't apply for this. And this happens, is a little quote, if you try to apply anyway. So this is a PhD student writing back saying that I wrote to him and said, could you give us some of this data so we can analyze this question? And he says basically that he recognizes, the professor recognizes that it's sensible to use the data for this purpose, but unfortunately it's politically not a good idea, and so they decline to share the data, even though it's anonymous data, right? Which is a suppression of research we're talking about. However, we did in fact find some data, and somewhat thanks to Thompson's blog. There was a paper with poverty shrinks the brain. Which they looked at brain size and poverty, and they see something is negative, which is completely expected also on genetic grounds, but that's not what the newspapers say.
That horrible paper, I used it as a bad example in my classes on.
Yes, it's obvious. Obvious. So the paper Noble et al. Is actually based on the PING dataset, which is a pediatric dataset that also has neuroscience in it. It's about 1,500 US kids. They oversample the non-white, so it's about 50% non-white, and 1,400 of these or so have genomic ancestry data estimated. They do have IQ and brain data, like a bunch of MRI stuff, and they have don't have any skin tone or any like discrimination self-report. So you couldn't really, even if you had the dataset, you couldn't rule out every possible confounder. There's a second one we found. We found a partial copy of this Brazilian dataset because someone published an article and they attached a partial copy of it. It's funny. And so it has about 3,000 people. It's from Brazil, it's birth cohort, so everybody's the same age, and it's a highly mixed population because that's how Brazil works. It has the real dataset has IQ, education, income, skin tone, discrimination, so basically has everything you need, except that the public one they put up, they don't have the IQs or the incomes or the discrimination. So we only have like a subset of Brazilian dataset. That's how we work with this. It's kind of like rogue science. However, someone found these and they gave me a hint and I analyzed them. And there's probably more of these to find, so I expect you should keep looking. I've been looking through all these websites of these Brazilian things to see if I could find the rest of the dataset, but I didn't find anything. So this is the ping dataset. It's just the basic thing of it. If you look at the sociological race, self-identified race or ethnicity, SIRE, you can see there's a bunch of these groups which I've coded in the standard way, so everybody who's self-reports being Hispanic is in the Hispanic category. If you report more than one thing of the others, you get into multi-ethnic. These are just kind of remainder categories, but two things are too small. White is nothing else. So you can see that in this sample, people who say they're white and don't say they're anything else, these are 97% European ancestry. So it's very close. If you say you're African American, your average ancestry here is 81%, which is about what you expect from prior studies. American Indians, 4 of them, so we don't care. Asians, pretty East Asian, but can also be Central Asian. So I'm guessing Asian here could mean Indian, or maybe Pakistani or one of these central ones. Hispanics are about 60% European, but it's probably going to be Southern European, and therefore slightly lower expected IQ. Unfortunately, they did not distinguish between Northern European and Southern European when they estimated ancestries, but you could do that. Multi-ethnic is kind of all over the place. So this is a main model, and on the left, the first one, we just fit a kind of standard model. The only thing we put in is the social race. So you can say that the gap from African American to the white reference group is 1 standard deviation, which is the usual value. Hispanics is 0.6, which is also close to the usual value. The other groups are quite small, so I'm just going to be ignoring them. And we also control for English as a first language, but it was always insignificant, so it's kind of pointless. However, if you ask, these are the genetic estimates of ancestry, we just add these to the regression model, and we see something funny. African American is now positive, although not significant, but positive. So it seems that all else equal, if you have the same amount of African ancestry and you say you're African American, actually you'll be somewhat above average, although could be a chance. All of these, as I recall, are non-significant. All the social ones are non-significant for IQ now, and all the race ones are large, the ones we care about. These two are the ones we care about. And these values, the b-tests here, are the non-standardized b-test, the slope we were talking about before, and this is the expected IQ in C-scores of a person with 100% ancestry of these. And you can see that I did not include European here. It's because the ancestry sums to 1, and you can't include predictors that have perfect multicollinearity. You have to do leave at least 1 out, and European is a natural choice because this sets European as the reference population. Okay, so by these data, this is the genetic gap for African Americans and Europeans in this one sample, and this is the one for Amerindian. So this one comes out to about 20 points, and this is 16 or something. And here, if we over-control, we add parental socioeconomic status as a control. We do the same thing, the social. You see that adding parental control, it shrinks the self-reported race by about 40%, which is consistent with prior literature. And the other ones are also smaller. And language still doesn't do anything. If we then add the genomics, we see that these social race ones are all tiny again. Fathers or parental socioeconomic status is again about the same. And the genetic ones, they become smaller, but not non-significant. So even if you over-control, you can still see the genetic pattern in the data. Of course, I didn't have any more variables we could control for here, and you could say that if only I controlled for 5 other confounders, then maybe maybe these values would go away. It remains to be seen when we find some more data, hopefully soon. This is if you visualize the data. The trouble with visualizing data here is that there's multiple ancestries in these people, and so you can't really plot more than 3 dimensions at once, and 2 is kind of easier. So if we subset to the group of African Americans that only have ancestry from European and African, it looks like this, and here's the slope as before. The slope is about the same in this subset as it is in the full, and is in fact, if you do the same thing for Hispanics with a regression, you get about the same slope as well, so there doesn't seem to be any like subgroup interactions with the slope. And if we do a fancy 3D plot, which is kind of difficult to read, we take every person whose ancestry is entirely a function of European, African, and Amerindian ancestry. This gives you about 800 people, so plenty of power. And you leave out European ancestry, and this gives you the 2 slopes. And you can see the European one here is about 0. And if you follow it down, this is the expected value of a person with 100% African ancestry here. It's about -1, close to what we had before, sampling error is there. And it's about the same over here. So that's how you have to kind of think about the data. Of course, in the full model, you have more than 3 of these, and it's not possible really to plot it. So you kind of have to generalize from this 3D plot to the possible 5D plot. So this is the Brazilian dataset. So the public version of the dataset, they don't have precise ancestries. They only give you quintiles. They say this person is somewhere in 0 to 20, 20 to 4, 40, and so on. But you see that the general pattern is there. This is an education measurement with an unclear scale, but it's an obvious pattern with more European ancestry that they're more well educated. If we do a regression model in the Brazilian data, we have about 2,900 sample size. If we just add sex control, all these people are the same age, so we don't need to control for age. We put in the 2 non-European ancestries. We can see that these have large values. This one is about equivalent to the slope one from before, so it says 1.15 and 1.6, or 0.6 in this. And the important thing to note here is that we did not add skin color, and the R2 is about 9.1, so 9.1% we explained right now. And then of education attainment in Brazil. If we then add skin tone, and this is self-reported, the R2 goes to 9.4, which is a tiny increase, and we see that the skin color one is significant here, it's highly significant, so it's probably not exactly changed. So there could be ways to interpret this is maybe there's some slight skin color discrimination in Brazil, at least in this birth cohort, that relates to education, or the use of these quintiles. It's introducing measurement error into your variables, and you can't tell which of these 2, or maybe both hypotheses are true from this data because the quintiles. But in any case, we do know that the skin color must be not very important because it only adds 0.2% variance explained or so. There are more studies of these on the way. There's at least one other researcher I found who did a similar study where they collected ancestry from self-reported people from 23andMe online. They just got some people to fill it out, and they have issues getting this published, as you could expect, in Tuning and Intelligence. So they're gonna get desk rejected from our friend Richard Heyer. But they also got consistent results for IQ, but the sample size is small, like 200. So I'm not naming it now because I did not get an agreement from him to name. These genomic datasets, they need to include the measures of non-genetic explanations, like skin color, even though technically that's genetic, so it's more like a reactionary thing, and discrimination. But even if you have these, you get questionable results. Suppose you find a self-report discrimination, and you see it's significant for IQ. So you see maybe they got discriminated against and got like lower IQs. Or maybe people who are dumber report more discrimination. How do you know, right? You can't tell from this data. And there are more genomic methods you could use that would be final, like admixture mapping, which I don't have time to go into. These are the references.
Thank you very much.